Hey everyone, I want to use this video to kind of talk you through homework number 7. So let's go look at it. Share my screen. All right, so the first problem is number 1. There's not much to say here. I just want you to be able to identify distributions by their shape. So this is uniform. You can tell it's a uniform distribution because it is a rectangle. Specifically, it's U38, right? U in parentheses 3, 8. You can tell because that's where it starts and ends. Second one on the homework is number 2. That's what an exponential graph looks like. That's an exponential distribution. Not much to say there. This is x between 2 and 5. So if you want to write this neatly, you want to write it kind of like this. This, by the way, some people mess this up and will do like a less than here and then a greater than here. Don't do that because that's saying that x is less than 3 and also greater than 5, or less than 2 and greater than 5, which is not, right? It's x is bigger than 2 but smaller than 5. And in fact, the way I would read this is x is between 2 and 5. I think between is the easiest way to say that, which that's clearly what it means here. So 2 and 5. So you want your answer to look something like put that on there somewhere. That one, yeah, like this right here. 5 was the next one. Oops. Oh man, my trackpad's not working very well. This is pretty clearly x is between 6 and 7 in an exponential distribution. All right, so from there, we went to number 12. Yeah, 12. All right, so if we want to find the probability that x falls in this shaded area, we really want to do base times height, right? So we would do 8 minus 6 to find the base. So this is clearly 2 units wide, and it's a 9th tall. So the area is 2 out of 9, right? That's all geometric probability is. It's just area, which is really convenient. That's why we graph things like this, by the way, is so you can have a visual aid. So 2 out of 9, 22.2%. Let's see what else we got. I should just use the arrow keys. My trackpad is betraying me here. What else do we do? 12, 13, 14? Yeah, okay. So same thing here. The area of this is 5 out of 8, or 62.5%. The area of this one, it's a little harder to tell. I'm going to assume that's 5.5 and 2.5, so that means this is 3 units wide. You can also count just like 3 to 5 is 2, and then I got a half here and a half there is 3. 3 out of 10, 3 out of 10 is 30%. All right, let's get to the interesting ones. What were the interesting ones? They start at number 75. Okay, so number 75, let's go look at that guy. Okay, random number generator picks a number from 1 to 9 in a uniform, oh come on computer, 1 to 9 in a uniform manner. So the thing that my students have screwed up most often in the past on this problem is that they're thinking, okay, 1 to 9, so they go y-axis all the way to 9, but that's not right, because 1 to 9, so there's only 8 numbers, or that's that the width there is 8, right? The bottom end is 1, not 0. So from here, this is pretty easy. X is approximately, or what they're looking for here is what's the name of this distribution, right? So it's uniform, and it goes from 1 to 9. So it's u, and then in parentheses 1, 9. Graph distribution is a rectangle. It's a rectangle from 1 to 9 with a height of 1/8, not 1/9, 1/8. So let me share up my answer for it. It looks like this here with my beautiful handwriting / drawing. When they ask about f of x in part C, what they're asking for is what is the name of the function, or what is the function defined as for the height, which is kind of a weird way of saying this, but it is how we think of this in algebra. It's 1/8, right? So it's 1/8 high. If you wanted to, you could do, so I just said that f of x was 1/8. I probably should actually have said something like this. Here, let me go here, right? So f of x is 1/8, but with the domain restriction that x is between 1 and 9, right? 1 less than x less than 9. something like that, and x is 0 everywhere else. I'm not that worried about that if you don't put the domain restriction on. It's technically not quite correct, but I'm not attempting to train you to be a statistician here, or a mathematician. What I really want is for you to understand, right? Just understand the basics. And so this is f of x is 1/8. It's only defined, or it's defined to be 1/8 between 1 and 9 and 0 everywhere else. But I'm not going to get into piecewise defined functions here. Like just f of x is 1/8 is what I'm looking for. 1/8, by the way, is 0.125. That's why you see these things right here, right? It's just easier to write 0.125. It looks funny with fractions and decimals mixed together, so I didn't. I just made them all decimals. All right, what else did it ask? Graph probability distribution function did that. f of x is 1/8. The mean is in the middle. The mean of a uniform distribution is in the middle, and the middle of 1 and 9 is 5, right? You can just average them to find that. 1 + 9/2. The standard deviation is b minus a over root 12. That's a thing that you can remember, but you can certainly put that in your notes as well. In fact, I would recommend you put that in your notes. And so you just type that into the calculator. It turns out to be about 2.3. Probability that x is between 3.5 and 7.25. Well, let me recommend that when you're doing this problem, that you draw on your the graph you made in part B, right? So that's a really good thing to do. Let me whip up a whiteboard here, right, so we can do that. I'm not going to do it every time, and certainly not on the written part of the homework. I'll do it here to show you what I mean, but you know, 1 and 9, and this is 1/8, and this 3.5 to 7.25. So 3.5 is over here somewhere, 3.5, and then 7.25 is like there-ish, 5, and there we're looking for this area. So you have to ask yourself, all right, well, how do I find this area? It's a rectangle, so it's base times height. So you do 7.25 minus 3.5, and you get 3.75. And you multiply that by 1/8 to get your area, right? And when you do that, it's not any nice number. It's some decimal. I don't remember what it comes out to be, so I wrote it down. 46.9%, right? About 46.9%. Same thing for the next part, where it asks about the probability of x being greater than 5.67. Well, we're going to go 5.67 up as high as it goes, which is 9, right? 9 minus 5.67 is 3.33, and so you do 3.33 times 1/8, and you get some other not particularly nice number, 41% or something. Yeah. H is an interesting one, I think. H is the probability that x is greater than 5, given that x is greater than 3. So what we're going to do is we're going to use the conditional probability formula, because of course this is a conditional probability, right? So what I'm going to do is I'm going to find the probability that x is greater than, so let me slow down a little bit here. I'm really going to find the probability of both of these things being true, and then divide by the probability of just that being true. So when I do that, let's go look at the picture, because it's actually much easier to see there. I'm going to clear everything and redraw it. All right, so we got 1/9. So the probability that there's 5, and there's 3. So if I'm looking for where x is both greater than 3 and also greater than 5, that's this. That's just this area here, right? This is where x is both bigger than 3 and also bigger than 5, because being bigger than 5 guarantees that you're bigger than 3. So really, this is just probability that x is greater than 5. So what I'm going to find here is this probability that x is greater than 5 divided by the probability that x is greater than 3. And you can do some quick math. This is 0.5, and this is 0.75. I'm not going to explain how to do that. I think it's clear enough from the previous parts. This comes out to be 2/3, or if you wanted percentage points, 66.7% or thereabouts. Right, but for conditional probabilities, we haven't abandoned the idea of conditional probability. In fact, when we get to p-values, conditional probability is super important. So yeah, don't forget about how conditional probability works. That's really the reason that's actually the reason I asked this whole question, was this one particular part. Oops, that's not the thing I wanted to share. I want to share up the book. Where's the book? There it is. 90th percentile. So for the 90th percentile, really what we're going to do is, let's go back to the whiteboard here. Clear everything off and redraw it. What we're really looking to do is figure out what this number is here, this question mark is, if I have 90% of the area to below and 10% of the area above. This is 1/9, of course, and then this is 1/8, like usual. 1/8. There's a couple ways to do this. I feel like the easiest thing to do is to realize that this number right here is going to be, I don't know how to say this. I want to think of this distribution shifted over to the left 1 unit so that it's at the x-axis, right? Or so that it's at the y-axis. And then when I'm done, shift it to the right. You can do that mathematically like this by doing, say, 0.9. So the area is base times height. So the base, here, I'm going to call this thing x right here, x. So the base here is this length, which is x minus 1. All right, so ignore the part about shifting to the left. I'm going to explain it in a different way, in a more understandable way, this way. So this base here is x minus 1, right? It's the right edge minus the left edge times 1/8, right? That's the area. So this is 1/8 times x minus 1, right? So that's what I'm attempting to solve for. You could also do like 9 minus x times 1/8 equals 0.1. That works just fine. In fact, I'll go ahead and do it that way once, just to make the point. So I have 0.9 times 1/8, 0.9 equals 1/8 times x minus 1. Multiply both sides by 8, and this is 7.2 equals x minus 1. So x equals 8.2, right? Add 1 to both sides. If I'd done that differently, I could have said 0.1 equals 1/8 times 9 minus x, right? That works as well. Multiply both sides by 8, I get 0.8 equals 9 minus x. And then what I'm going to do is I'm going to add x to the left and subtract 0.8 to the right and get x equals 9 minus 0.8, which is 8.2. So same either way. Algebra works fine either direction. The trick here is that you just want to make an equation saying, well, this area is equal to base times height, right? And so that's what this says. The area is equal to, I guess I wrote height times base, but you get the idea, base times height. And solve that way, right? That's the simplest way I know of. There isn't a nice, simple, like, just plug it in formula. You pretty much have to do algebra. I guess we could figure this out, right? You could do like area equals height times x minus a, where a is the left endpoint, and then solve in general for x. It honestly just seems easier to do this every time. It's not like you're going to have to answer this question 1,000 times. That you need a formula to just plug in repeatedly to just do this little three-step process. At least I think that's the easiest way. You're welcome to find your own process if you like it, but I like this one. All right, so back to the book. Yeah, so it's the 90th percentile. I forgot what the next problem was on the homework. It was 77. Okay, so 77 is another uniform distribution problem, right? So 77, subway train arrives every 8 minutes during rush hour. Come on. Sorry, my track guides really drive me crazy here. We're interested in the length of time a commuter must wait for a train to arrive. The time follows a uniform distribution. You got to watch out for phrases like this, right? It's really easy to when the how can I say this? It's really easy to kind of mentally check out as soon as you see this, right? This or possibly this. I don't know exactly, or possibly the second sentence there. I don't know why it is, but it's quite easy. Hello, computer? won't highlight for me. Second sentence is what I'm trying to highlight here. It's actually quite easy to ignore this last sentence, and so if you find yourself doing that, don't. I mean, I don't have any better advice for you than that. I've had to help a lot of students do that and not start jumping to the problem before, or not start jumping to the parts before they read the whole problem. I know this sounds like silly and pedantic and unnecessary, but I really have seen people do this a lot, and they'll literally come ask me on a test, how do I know what distribution to use when it says in the problem, use a uniform distribution, and that they won't notice. So yeah, I don't know, just read everything, I guess, is read really carefully is what I'm trying to say here. So X is literally the thing they said. We are interested in the length of time a commuter must wait for a train to arrive. So X is the length of time that a commuter must wait for a train to arrive, exactly like you think it would be. X is U08, which when I made this homework, I hadn't noticed that it was the same width as number 75, both 8 units wide, but whatever, it doesn't change very much. So graph, it's a rectangle from 0 to 8, height of 1/8. F of X is 1/8. Mu is 4 and sigma is the same as it was before because it's got the same spread as problem 75. So 2.31, I think is what it was. Right, still 8 over root 12. Find the probability that the commuter waits less than 1 minute. So we're asking for, so we'll draw this one, but this one's actually really, really easy. You barely even, I don't know why I was erasing this. You barely even have to do any work. In fact, you really don't. Right, so our distribution looks like that, where this is 8 and this is 0. And the question asks, what's the probability they wait less than 1 minute? Well, if this is 1/8 here, that is 1 times 1/8 is the probability. So it's 1/8, so 0.125 or 12.5%. And then the next question asks about what's the probability they have to wait between 3 and 4 minutes. And I haven't drawn this very well to scale, but that's between here and here, right? That's this stuff. So that's also a base of 1 and a height of 1/8. So it's also 1/8, right? So the area is the same for the same width, no matter where you are in the distribution. That's not true in general, by the way. That's just for uniform distributions, not true for like exponential. Yeah, so that's between 3 and 4 minutes. It's also 1/8. 60% of commuters wait more than how long for the train? So that is an easy question to mess up. So it's saying 60% wait longer than a certain amount of time. And so it's not obvious how you should interpret that, right? So it's one of two things is obvious. It's either like this with 40% on the left and 60% on the right, or like this with 60 on the left and 40 on the right. And the question is really which one, right? Like which one is it? It's got to be one of those two. And so when we look at it, let's go read it again. So it says 60% of commuters wait more than how long for the train? Well, more than is to the right. So this says 60% is to the right, and therefore 40% is to the left, of course. So that is, if 60% is to the right and 40% is to the left, then we want this one. We're looking for the 40th percentile, right? So let's get rid of this guy right here. Ooh, not that one. And so we just find the 40th percentile sort of the same way we did it in the previous problem, where we just this is 0.4 here, 0.4, and I say that this guy's x. We say 0.4 equals the base, which is x. It's x minus 0, so x times 1/8. So x is 3.2. Right, you just don't forget your algebra. Gotta use it a little bit here. So x 3.2, and there you go. That's it. All right, so the next problem was, oh my gosh, come on, that's bad. 86, and we got 86 and 89. So 86. Suppose the length of long distance calls is known to have an exponential distribution with the average length of a call equal to 8 minutes. All right, so remember that the, what is that thing called? So the mean and the decay factor, what do they call it? They call it the decay constant, are inverses, or inverses in the right word, reciprocals of each other. So if the mean is 8 minutes, then the decay constant is 1/8. And so the random variable is, okay, when we get to part C, but x is the length of time that a long distance phone call lasts, exactly like you think it would be. X is continuous, and you can tell because time is continuous. Time can be subdivided in infinite amount of times. Maybe that's not the best way to think of it. Time can be anything in a range, right? So a long distance phone call could be 0 minutes all the way up to, you know, theoretically infinite minutes, right? There's no theoretical upper limit other than, you know, somebody's lifetime or whatever, but don't even worry about that. Just 0 and up, basically. And so since it can be anything within a range and not just certain discrete values, it's continuous. X is what they're looking for here is the name of the distribution. So it's exp of whatever, in this case, it's exp of m, not mu, where m is your decay constant, so it's 1/8, right? Exp of 1/8. So you want to write that something like this, right? X is exp of 1/8. Oop, I used the wrong symbol there. This should be a tilde. There we go. That's the thing I meant. So the mean, they literally told us what the mean was. Mu is, well, mu is the average, right? And we know that the average length is 8 minutes. So mu equals 8. In an exponential distribution, the standard deviation also equals the mean. This is not exactly a coincidence, but it's something that's not true in general for distributions, but it's true for exponential distributions and for Poisson as well. When we do those a little bit later, or did we do those before? Oh yeah, they're discrete, so we did them before. Yeah, so also Poisson also has that same property. Nothing else does that I know of. There's probably some other distributions out there that do, but I don't know what they are. If we sketch a graph of it, here, let's I'll sketch a graph and we'll find the probabilities here. Less than 9, greater than 9, and between 7 and 9. So if I sketch a graph of an exponential distribution looks something like this, where this is right here. This is the decay constant. It goes up to the decay constant. Remember that this is f of x equals m e to the minus mx. So this thing right here, when x is 0, that part is 1 because it's e to the 0 power, which is anything to the 0 is 1. And so you multiply by m, and the thing that you get is just m. Let me undo that. So that means that this goes up to a height of 1/8 right here. And they said, yeah, so there's 8. It's the mean. I'm not putting this in I know it kind of looks like this is in the middle, but that's just where the mean is. It's not like this goes on forever to the right, so this isn't like the middle of the distribution. It's just the mean. The questions ask for greater than 9 and less than 9. So here's 9. So to the left, well, to the right is easier to define. So let's let me get a different color here. So to the right, if you'll recall, that area is e to the minus m k, which in this case, k is 9. K is just the dividing line. So this is e to the minus 1/8 times 9. And then the area to the left is 1 minus that, of course, because the total area is 1. So this is 1 minus e to the minus 1/8 times 9. I hope everyone's clear on that being 9/8. So this is 1 minus e to the minus 9/8. I don't remember what those numbers are. Let's quickly look at them. Of course, post them here. What is that, like 67.5% and 33.5%. So 67.5 to the left, 33.5 to the right. What else did they ask? Between 7 and 9. So this one takes a little bit of explanations here. So I'll show you how I did it, right? So I did it like this. But it's not necessarily obvious from that equation how I got that. So what I did was I visualized, here, I need a new drawing. It's too messy here. So they want 7 to 9. I think the easiest way to do that, so here's 7 and here's 9. Don't worry about the fact that it's not very well to scale. Right, so this is what I'm looking for. So we don't have a formula for that. So the easiest thing to do is either calculate everything up to 9 and then subtract off the stuff that you don't want, which is everything up to 7. Or I actually did it to the right because the formula is slightly easier. The formula to the left has a 1 minus it, and the formula to the right doesn't. So I do it to the right when I have these options. So we do the area to the right of 7 minus the area to the right of 9. And that gives you like 9% or something like that. And if 25 phone calls were made one after the other, what would you expect the total to be? Well, so let me just say this as many times as I can. When the word expect appears in the question, they are asking for the expected value almost certainly, right? Determined from context, English can be weird, but in general, when they say expect, you think expected value. Expected value is average. The average is 8 minutes. If we have 25 phone calls that each average 8 minutes, the average for each one is 8 minutes, then the overall average is 8 times 25 minutes, or just 200. So about a little over 3 hours. So that's it. You literally just take 25 and multiply by 8 to get the then 89 was the last one on this homework. By the way, I would love some feedback on whether you feel like the homework is too long or too short or whatever. I feel like I might be making them too short, but I don't think I get too many complaints about shortness of homework. Anyway, yeah, let me know what you think. So the time after reaching age 60 that it takes an individual to retire is exponentially distributed with a mean of 5 years. Now, when they say approximately and about 5 years, just take that to mean exponentially distributed with a mean of 5 years, right? It feels a little weird to just ignore all the caveats, ignore the approximately and ignore the about, but that's without further information. That's just the easiest. That's just the right thing to do there, right? If the person stating the problem says, this is basically exponential and the mean is about 5, just run with it. So suppose we randomly pick one retired individual. We're interested in the time after age 60 to retirement. So interestingly, there are a few problems with this problem, and it's something that your authors do kind of often, which is a little annoying. Not everybody retires after 60. Some people retire before 60, in which case they would be negative years. And exponential distributions don't account for negative answers. There's a few other potential problems with this, but the whole point of this homework assignment is to practice with exponential distributions, so we're going to ignore all of that nonsense, and just pretend that this is exactly what they meant, and this is perfectly correct. Yeah, so we're just going to assume this is number of years after 60 when they retire. So keep in mind that if you retire at 60, that means that X is 0, because you retired 0 years after 60. If you retire at 65, X is 5, right, which is the mean retirement age, mean of about 5 years. So when X is 5, that means the person retired at 65, and vice versa. And so if someone doesn't retire until they're 102, right, then X is 42. I hope people aren't still working when they're 102. All right, so define the random variable. X is the number of years after age 60 that a person retires. X is continuous because time, just like in the last problem, is still continuous. X is approximately an exponential distribution, so exp of 1 over mu. Remember that m is 1 over mu, mu is 5, so exp of 1/5. Mean, they told us is 5, standard deviation, same as mean, 5. Again, that's kind of unique to exponential distributions. Don't think that mean and standard deviation are always the same, because they're generally not, but in exponential distributions they are. Draw a graph, label the axes, find the probability of a person retired after 70. All right, let's go draw a graph. Let's get a new page. So we got a graph that looks something like this. And this is 0. So keep in mind that I'll put 5 here. And again, you don't have to put the mean on. I just like to put it on for sort of a sense of scale, basically. This goes up to 1/5. And this is f of x equals 1/5 e to the minus 1/5 x. Okay. And again, to the left is 1 minus e to the minus mk, where k is whatever the cutoff is. And to the right is just e to the minus mk, where m in this case is 1/5. 1/5, by the way, if you're putting in your calculator and want to make it easier on yourself, it's 0.2. Feel free to convert to decimals first. It's a little easier to type. I forgot what to ask. I got too caught up in drawing and talking. Person retired after age 70. So age 70 is x equals 10, right? This is 65. So here's 60, 65. 70 is right here. 10. So that's what we're looking for. That is e to the minus 1/5 times 10, or minus 2. So just to the right of this is e to the minus 2. Whatever that comes out to be, it's like a 1/7 or something, I think. Like 14-ish%, if I remember correctly. Yeah, you can see my picture there. Yeah, a little over 14%. That's about 1/7. Part H is kind of interesting. I actually like this question a lot. Now, you can certainly do this in an uninteresting way, right? We can calculate the probability of people retiring before age 65 and the probability of them retiring after age 65. So area to the left of 5, area to the right of 5. But we can also do it without doing any work, which is my favorite kind of problem. The one where you just think about it and then you know the answer and you don't have to do anything, or you don't have to actually, do anything, do any calculations. That's what I'm trying to say. So I'm going to redraw this. I'm going to draw another one here. It's the same thing, right? So if my mean here is 5, notice that my distribution is right skewed. Right, it's skewed to the right. So that means, so the median, if 5 were the median, that would mean that 50% was to the left and 50% was to the right. But since the distribution is skewed to the right, that pulls the mean to the right. That means that the median is somewhere over here. Right, that guy's the median. And that's where 50% is to the left and 50% is to the right. Well, if I just look at this, the mean got pulled to the right. So there's more than 50% to the left and less than 50% to the right. There you go. So if they're asking about whether more people retire younger than 65 or older than 65, more people retire younger than 65. At least according to this, which does not sound right to me. Most people I know tend to keep working. Anyway, according to this, more people retire before 65 than after. Right. I think I went and found the numbers. You can find the numbers yourself. They come out to be about 63% left and 37% right. In a room of 1,000 people over age 80, how many do you expect will not have retired yet? So in other words, so the people who have not retired by age 80, where am I? The whiteboard here. Wait, hang on. Is it not sharing? Oh, there we go. Sorry, my computer wasn't switching. So the people who have not retired by age 80 are these people. The ones who are, there's 5. So age 80 means that X is 15. So all the people to the left of this have already retired, right? Their retirement age was less than 80. The people who have not yet retired are those whose retirement age is over 80, right? If everybody's 80 in this room, then those who have not yet retired have a retirement age greater than 80. That is just this part over here, right? So that's just what the probability of being over here is, which is e to the minus 1/5 times 15, which is e to the minus 3, times the number of people in the room, which is 1,000. So it's really just 1,000 e to the minus 3 is what this number is, which turns out to be about 50. And again, I suppose I should probably do this and just show you how you find that. I know some people have trouble putting in e to the power in your calculator. There's an e to the power right here, right? So I would just do 1,000 times e to the power of negative. Oh, and by the way, I don't know if you can tell, but my mouse didn't move over the negative sign there. there's keyboard shortcuts for everything if you're using the VMware version of this calculator. Here, let me show you. So if I want to hit clear, the keyboard shortcut for clear is backspace. So notice my mouse moves over here. I'm just going to hit backspace and it will get rid of everything, right? And so if I want to do 1000 e to the power of negative, here, let me type it again. 1000 e. Now the shortcut for the second key is F6. I'm on a laptop that doesn't have nice F keys, so I usually just press this with the mouse. But if you want to, you can just hit F6 and it'll do second for you. And then F1 through F5 are these things up here, and you can actually tell what the keyboard shortcut is based on whatever the alpha key is, right? So if I hit like alpha program, it'll make a C, right? That's not what I want here, right? What the thing that I want is I want the negative sign here, right? This negative right here, which is question mark. So if I want to do e to the power of, so here's e to the power of, and again, I could hit F6 then S, and it'll give me the thing I want. Then to get the negative sign, I hit question mark. Oops, sorry, question mark like that, and that gives me my negative sign. So negative, and it was 1/5. So here I'm just going to put in parentheses 1/5 close parentheses times 15. Right, so I can do this all on the keyboard without having to mouse over things, which is kind of nice. I get used to that. You get faster with it if you use the keyboard shortcuts. So like 50-ish people, right? 49.8 people, so about 50 people. I believe that was the last problem. Is that correct? Let's share this back up. Not have retired. Yes. So the people whose retirement age was over 80, right? So was about 50 people. So that's the answer, and that's where I want to go ahead and leave this homework. All right, I will see you guys in the next video.